This is our first video on gases and gas laws, and is going to serve as an introduction to some of the other things we're going to do with gases in this chapter. So the very first thing we want to talk about with gases is something called kinetic molecular theory, or sometimes you just hear it as KMT. So what kinetic molecular theory is it's a way to visualize what's happening with the gas particles. And it's a series of assumptions and simplifications that give you a very clear view of what's happening with gas particles and how they're behaving. If you can picture what's happening at the particle level, it makes all of the laws and the relationships much easier to understand. So some of these assumptions involve some simplifications, meaning some of the points we're going to make here aren't necessarily 100% true. We're assuming that they're true because if you assume they are true, they make a much clearer picture of what's happening. And the first assumption we make when we're dealing with kinetic molecular theory is gas particles are going to be treated as points. So when we say something is a point, we mean a point mass. What we mean is that the actual volume of the individual gas particles themselves is so small, we're basically going to assume they're zero. Now, in reality, we know that there are volumes for these gas particles, and that can come into play later. But in the simplest view that you can take is at first, don't worry about the volume of the individual particles. The second point in kinetic molecular theory that we're going to look at are the attractive forces. And we're going to assume, and again, this is not 100% true, but we're going to assume that there are no attractive or repulsive forces between the particles. Here's one where, again, this is a simplification. It's not 100% true. There are attractive forces between the gas particles. It's just that they are very, 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 very weak. Being they're so weak, most of the time we can ignore those attractive forces. And if we're able to ignore those attractive forces, that's going to paint a much simpler view of what's happening with these gas particles. Because we're going to ignore attractive or repulsive forces, we're able to visualize each particle acting independently of the other particles around it, which makes for a much simpler view. Kind of our third thing we think about when we're dealing with gases is collisions are elastic. Now, elastic collisions is kind of a big physics term. We don't want to necessarily get into the physics of that, but you can think of it as perfect rebounding. Whenever the gas particles hit something, they're just going to be deflected off of that. They're going to come out of that deflection with the same speed, just bouncing off of that collision that they had, whether that's with the walls of the container or with another particle. One way of visualizing this is if you think back to a very, very old computer screen, and you think about the old Windows screensavers that kind of have the multicolored balls just floating around until they hit either another ball or the side of the screen, then they would just bounce off and keep on doing that. That's kind of what you're looking at for these gas particles. Kind of our fourth thing we think about in kinetic molecular theory is that the kinetic energy of the particles is directly related to the temperature. So what that means is if you increase the temperature, you're going to increase the kinetic energy. And that usually shows up as you increase the kinetic energy, the particles are going to be moving faster at higher temperatures. So these four assumptions we make in kinetic molecular theory are things you want to have in the back of your mind all the time when you're dealing with gases. I'm going to talk real quickly about the four properties that we have for gases. These are how we go about describing gases. These are our observables. These are things you can record data on. These are things you can commonly talk about. And you're familiar with a lot of these: pressure, volume, amount, temperature. We're familiar with these. These are the properties we're using to describe a gas. And what we're going to do is we're going to talk about these properties and then talk about how they're going to be related to each other. So these have relationships with each other. We're going to talk about them qualitatively as well as quantitatively. So let's quickly go ahead and review our 4 gas properties. First one, the one we're going to spend the most time on, is pressure. We're going to spend the most time on this one is because this is a property we haven't really talked about much in other situations. When we talk about pressure for a gas, what we're talking about is pressure is going to be the force that's exerted when the particles hit the walls of the container that's holding the gas. Just like if you kind of push your hand or have your hand hit a wall, your hand is exerting a force on that wall. If you think about this on a smaller scale, that's what the gas particles are doing all the time. That force that they're exerting when they're hitting the walls of the container, that's the pressure. There are tons and tons and tons of different pressure units. And each discipline kind of has their favorites. I just want to quickly kind of talk about some of the ones you're familiar with. We have the weather app on your phone. You're familiar with inches of mercury. We often don't deal with inches so often, but when they say the pressure is 29.98 today, well, they're talking about inches of mercury, the height of mercury in a barometer. Millimeters of mercury you often hear used a lot more just because it's metric. Sometimes you'll also hear about bars and millibars for weather and meteorological things. Sometimes when there's a tropical storm or a hurricane, they'll talk about the pressure inside the eye of the storm being 960. Well, the units they're using there are usually millibars. Some other pressure units we might be familiar with: PSI, pounds per square inch. You're familiar with this in your car tires when it says inflate to 35. That's 35 psi, pounds per square inch. Pascals, sometimes used in engineering disciplines. Our chemistry favorites are millimeters of mercury, which is a named unit and is referred to as a torr, and atmospheres. Those are the ones you see most often in terms of chemistry. You don't have to memorize any of the conversion factors for these. All the conversion factors between pressure units, if you ever have to change between pressure units, are going to be provided for you. So that's pressure. Our next unit is volume. We don't need to spend so much time with this because we're more familiar with volume and what it does and what it is. We've spent a lot of time talking about volume previously. Volume, just like for a liquid or a solid, is how much space is occupied. You can use any volume units you can really imagine. Usually we use metric though. So if you have a small amount of gas, milliliters, more gas, liters, whole bunch of gas, kiloliters. If you're doing even bigger things, you might get into megaliters, but generally volume, you're looking at metric. Our next property is amount. And we're actually going to spend a little bit of time dealing with this because previously, whenever we've dealt with a liquid or solid, you've kind of used amount and volume almost interchangeably. I mean, think about it. Amount, you may have read in your laboratory manual, the amount of water you need in an experiment is 10 milliliters. Well, they're using amount and volume interchangeably. And you can do that for a liquid or a solid because those volumes aren't really going to change. Those are condensed phases. But gases are compressible and expandable. So amount and volume mean two very, very different things when we're dealing with a gas. Volume is how much space is occupied, but amount is how much material is present. So usually how much material, we want to think about grams and moles. And here's where gases are going to behave very, very differently than liquids or solids. For a gas, I can maybe have 2 grams of material be that much volume, or I can maybe change the conditions and that 2 grams of gas might have a much bigger volume. In each case, the amount would be the same, 2 grams, but the volumes would be very different. So we want to make sure when we're dealing with gases that we're really treating amount and volume as different. Our last property that we want to talk about is temperature. We saw in kinetic molecular theory, this is describing how fast these particles are traveling. We know we have 3 different temperature scales, Fahrenheit, Celsius, and Kelvin. We're most often looking at Kelvin when we're dealing with gases. And the reason for that is that's that absolute temperature scale. Just as a quick review, remember, absolute means there's no negative numbers. And that's going to be important when we're doing calculations, when we're using temperature values in equations. For example, if you look at minus 20 degrees Celsius versus positive 20 degrees Celsius, there's a 40-degree difference in there. But if you were to just stick negative 20 into equation and then stick positive 20 into that equation, you don't really see a 40-degree difference there. You're going to get out 2 values for something else, one positive, one negative. You're not going to see that true 40-degree difference. That's why Kelvin ends up being used, because in Kelvin, a 40-degree difference looks like a 40-degree difference. 253, 293, there's that same 40-degree difference. Now we're able to see it much more clearly. So we're going to think about using Kelvin for our temperature. What I'm going to do next is go through a series of gas laws. What's going to happen in each of these laws, in each gas law that we have, we're going to look at how 2 of those 4 properties that we just talked about are related. For those 2 properties, if we're trying to see how they're related, we can't be fidgeting with the other 2 properties at the same time. There'd be too many variables. You wouldn't be able to see a clear cause and effect. So that's what we're looking at, is 2 properties are always going to be held constant, 2 properties are going to be changing. So our first law is Boyle's law. And Boyle's law says there's an inverse relationship between pressure and volume. Remember what an inverse relationship was. Inverse is opposite. As one increases, the other decreases. In this, amount and temperature have to be the things that are held constant. We don't really need to worry about the math equation associated with that. We're not going to do any calculations with that, so we can just kind of get rid of that. I want to show you an illustration kind of dealing with that. We get pressure when the particles are hitting the walls of the container, as shown in the figure. In the one on the left, there's a much bigger volume. That means the particles are going to hit the walls of the container less often. Larger volume, smaller pressure. On the right, what you're seeing is a much smaller volume. Same number of particles, they're still traveling the same speed, but now you have on the right a much smaller volume. Being you have a much smaller volume, you're going to have more collisions between the particles and the walls of the container because there is not as much room. If you're getting more collisions, you're going to have an increase in pressure. So you see that inverse relationship between volume and pressure. Our next gas law we want to talk about is Charles' law. Charles' law is a direct relationship, this time between temperature and volume. Remember, in a direct relationship, as one property increases, the other one is also going to increase. So if we're having temperature and volume be related to each other directly, that means amount and pressure have to be held constant. And you're familiar with an example of this already. We're familiar with how balloons work. Balloons are a good example of Charles' law because they keep the pressure and the amount constant. When you take a balloon and you expose it to heat, well, sometimes you think the balloon pops. Well, it can. But before it pops, if you warm up a balloon gradually, you're going to see that the volume of the balloon is going to get bigger. And that's what you see on the right. You probably had the experience of taking a balloon out in the cold, maybe in the winter. As that air or that gas inside the balloon gets colder, the balloon shrivels up and gets much smaller. So we're familiar with how balloons work. Balloons are a good example of Charles' law. Next gas law we want to deal with is Daltons Law. For this specific law, a lot of credit gets delivered in different ways for this. Some people talk about this not as Daltons Law, but as Gay-Lussac Law. Some people just attribute this law as a different example of Charles' Law. Your book gives the credit to Daltons, so that's kind of what we're dealing with. So Daltons Law says that there's a direct relationship between temperature and pressure. So in a direct relationship, as one increases, the other increases. That means our other two properties must be held constant. So amount and volume are going to be held constant in this. So here we have a little bit different picture. Here we have a fixed volume container. Same number of gas particles. On the left, they're more at room temperature. On the right, you can kind of see the flames. We're heating this up. So what you're seeing is as we're applying heat to this, you see the speed of the particles increasing. That's the little kind of tails that they have. On the left, gas particles aren't very hot, very small tails, trying to show you that they're not moving very fast. On the right, the tails trying to show you that they're moving a lot faster. So as you apply heat, the volume didn't change, the amount didn't change, but as you apply heat, the particles are moving faster. What that means is two things are going to happen. If they're moving faster, every time they hit the walls of the container, they're going to hit with more force. Think about barely touching a wall versus really punching a wall. When you really punch a wall as opposed to barely touch a wall, you're exerting a lot more force because your hand is moving much faster. So as they increase their speed, they're going to hit the walls of the container with more force. Remember, they're also bouncing around. So not only are they going to hit with more force, they're going to bounce off and hit again. So you're getting collisions that are more powerful with the walls of the container, as well as more frequent collisions. That's going to increase that pressure. Our next gas law is Avogadros Law. Yes, same Avogadro of Avogadro's number fame. Avogadros Law talks about the direct relationship that we find between amount and volume. Again, when we're dealing with amount and volume, as one increases, the other one's going to increase. Temperature and pressure are constant. Here's another balloon example that we're very familiar with. When you blow more air into a balloon, it gets bigger. The volume gets bigger. You let the air out of a balloon, it's going to get smaller. So we're pretty familiar with Avogadro's law because we're familiar with how balloons operate. So those are 4 individual gas laws. We're not going to do any calculations individually with these, because what we can do is we can combine these gas laws. So what we're going to talk about next is sometimes called the ideal gas law. I kind of put the older terminology that you still sometimes see used here, which is the combined gas law, because you can see all of those individual gas laws we just talked about in this ideal gas law. So the ideal gas law combines Boyle's, Charles, Daltons, and Avogadro's law into one mathematical form. And here it is. PV equals nRT. So I want to show you those relationships that we just saw. P is for pressure, V is for volume, N is the symbol we use for amount. That would be moles in this case. Let's skip R for the moment. We'll get back to R. And T is temperature. R ends up being a constant value that helps relate all of the other units to each other mathematically. You might look and say, man, that's some strange units. liters times atmospheres divided by moles and Kelvin. Well, it has such strange units because of the standard units that you would use for the other properties. Well, pressure is going to be in ATM, volume in liters, amount in moles, temperature in Kelvin. So you would end up seeing those same units as part of that constant. Let's talk about how we can actually see all of these laws in the ideal gas law. First, Boyle's law. Boyle's law, remember, says you have an inverse relationship between pressure and volume if you have constant temperature and amount. Well, in the ideal gas law here, you see that pressure and volume are on the same side of the equation. If they're on the same side of the equation, and everything else on the other side of the equation, N's constant, T's constant, R's constant. If pressure goes up, to keep the right-hand side the same, volume would have to go down in that case. So you're really seeing Boyle's law in here. You can see the other gas laws in here as well. The other gas laws you can see in here, you can see Charles' law in here. If I do this in a different color, I'll do this one in blue. Charles' law says you have a direct relationship between Charles' law says you have a direct relationship between volume and temperature. Well, here's volume, here's temperature. Notice how they're on opposite sides of the equation? That's going to be a direct relationship because pressure's constant, amount's constant, R's constant. If I increase one, I need to increase the other one as well. Daltons law, you can see Daltons law in here too. Daltons law, direct relationship between pressure and temperature. Direct relationships, you're going to see things on opposite sides of the equation. Here in purple, pressure and temperature are all on opposite sides of the equation. Well, if volume, amount, and R are all constant, well, then if I increase one, I better increase the other one. Kind of the last one we want to see in here is Avogadros Law. Do this in the orange. If you look at Avogadros Law, direct relationship between volume and amount. Well, volume and amount, opposite sides of the equation. The other things still have to be constant. Constant pressure, constant temperature. R is constant. Opposite sides of the equation. If I increase one, I can increase the other. So being we can combine all these gas laws into one, we don't need individual equations for Boyle's law, Charles' law, Daltons, Avogadros law. You can write them, you can do problems with them, but instead, our mathematical problems are going to be based upon this ideal gas law. We won't be doing any mathematical calculation examples in this video. Those will happen in a future video. I want to just show you some other things that can be seen in the ideal gas equation. You can get some other things in here that you're familiar with. So the first thing you can really get in here is you can get in mass and molar mass in here. Well, we know that N is moles. If I highlight that in red, N is moles, and we know how to calculate moles. Moles would be grams divided by the molar mass. That'd be your MM. So if I just substitute that in for the moles, that N for the moles, substituted in for grams divided by the molar mass, I'd have this third equation here. Now I can see the grams and the molar mass in there. Maybe there'd be some use for that derivation of the equation. There's some other things we can potentially get in here. If I do a little algebraic manipulation, so going from the third line to this fourth line, if I divide both sides through by the volume. So I divide by the volume, so my volume's not appearing here on the left, but now it'll be on the denominator in the right. I see another potential substitution I can make. I have grams divided by volume. If I kind of highlight that in red, grams divided by a volume, well, that's a mass divided by a volume. We know mass divided by volume, that's density. So I can make that substitution as well to get this kind of 1, 2, 3, 4, 5, 6 line here. That very last line, P equals dRT divided by the molar mass. Kind of one important note about if you are ever using this last equation, the density here is in grams per liter. And that's a little bit different than what you're used to. A lot of times in liquids, you're talking about the density being grams per milliliter. A couple reasons for that. One, gases aren't very dense, so having a bigger volume kind of makes sense to keep the numbers a little bit easier to deal with. And just coming out of where we started with the ideal gas equation, our volume was in liters. So here there's some other things we've talked about previously, moles and density, that can be cleverly substituted in to this ideal gas equation. Kind of our last thing we want to talk about is another gas law, not related to the ideal gas law, but as we're kind of doing a qualitative review of gas laws, I wanted to bring this one in here as well. And again, we'll do a numerical problem with this in a different video, but I just wanted to introduce in this one, this is Dalton's law of partial pressures. So in Dalton's law of partial pressures, what it's saying is in a mixture of gases, the total pressure is equal to the sum of each individual gas's partial pressure. So that's a lot of words. It's actually easier to talk about more in equation form. Your total pressure is going to equal the sum of all of the other individual gases. If I had 3, I'd have those 3 individual gases, individual pressures would be the total. If I only had 2, well, I'd only have 2 here. If I had 7, I'd have, some more partial pressures for the gases here. Dalton's law is real easy to deal with as long as you remember 2 things. First, the sum of the parts is equal to the total. That's no different than anything else you're used to dealing with. The total had better be the sum of all the things that are going in to contribute to it. The only other thing to really worry about with this are units, and units are very important for this. Everything must be in the same unit. If you're going to be adding and subtracting different things, they have to be in the same units. You can think about this the same way of if you had 3 objects that you're trying to figure out what the total mass was or the total weight was. If one was in ounces, one was in grams, and one was in pounds, you couldn't just add up the numbers because that wouldn't have any meaning because the units don't match. You would first have to convert those into a common unit. Same thing is going to apply here for Dalton's law of partial pressures. For Dalton's law of partial pressures, each of your pressures has to be in the same unit. So you might have to do some conversions to get things into the same unit. You can't just randomly add PSI plus atmospheres plus torrs and expect that number to mean anything. First, you would have to convert everything into the exact same unit.